Okay, welcome back to hybrid mode for the late announcement about this being hybrid. Today's speaker is our very own, one of the three Origins organizers, Chenliang Huang from LPL, University of Arizona. So Chenliang got a PhD at University of Virginia, right? And you worked on the hot Jupiter atmosphere. And actually, that was an interesting, you worked with the interacting supernovae as well. Yeah, that was really cool to find out. And then I had a postdoc at University of Nevada, right? Working on modeling of interior structure of terrestrial super Earth planets. Now Chenliang is here in LPL as a postdoc. You work with Koskinen. Okay, let's welcome Chenliang. The floor is yours.
Thank you for the introduction, Serena. And very glad to have a talk today. So today I'm going to talk about the hydrodynamic study of the escape of metal species and excited hydrogen in the atmosphere of hot Jupiter WASP-121b. So this work is done in collaborate with my postdoc advisor, Tommy Koskinen, and also collaborate with Panagiotis Lavas and Luca Fossati. So probably you all heard that the NASA archive just announced that they confirmed over 5,000 confirmed planets last week. So people use this database to make a population diagram like this, the size of the planet over the period. There are several features on this. One notice is the subtropical desert with the short period planets and a couple of Earth radius over here. Another is in the radial. There is a small dip at about 1.8-ish Earth radii. There are several explanations for that. For example, there are photoevaporation, there are core powered mass loss, there are initial gas accretion, etc. So understanding all this process, one important tool is to study, observe, and model the upper atmosphere. Among these, specifically for the photoevaporation, which is the Lyman continuum flux that hit the upper atmosphere and convert the heat to the escape. So that's a key process we need to model in the upper atmosphere model. So it's specific need for study the photoevaporation process. Okay, and so recently, probably because of the data diversity, there's much more focus on the molecular features in the lower atmosphere. So we have studied the upper atmosphere, which is quite different in several ways. The first, at upper atmosphere is mostly atomic feature or ionized features, and then the scale height of the upper atmosphere is much larger, so the signature in the like infrared molecular band is the transit depth is very small. Typically, we combine a lot of features together, use like cross correlation or something to study them. But for the atomic features, typically we have much larger scale height and it blocks much larger fraction of the light. So it's possible for us to use high resolution transmission spectrum to study individual profile, individual transit lines, and then to construct the model for the whole atmosphere. And also in the upper atmosphere is really non-LTE, it's non-isothermal. So it's quite different from modeling the lower atmosphere to the upper one. So there are several features commonly used to study this upper atmosphere. The oldest one is the Lyman alpha showing on the left. So we see the out of transit curve, and compared to the in transit curve, the Lyman alpha, the ground state hydrogen can block like half of the starlight due to the planet GJ436b. It has like comet tail structure, hydrogen tail. One problem of this feature is because of the geocorona emission and also the SM absorption between telescope and the system, we cannot see the center part, which naturally carries most of the information. So unfortunately, we can't see them. In addition, because of the nature of the complicated resonance scattering of the Lambda alpha process, it's quite difficult to really construct the atmosphere property from these Lambda alpha features. Another feature that's very hot recently, roughly past 5 years, is the helium 10A30 lines. So it does not have the problem of block the line center, and it's also tracing the very abundant elements. So we got a talk from Shreyas Pragada last semester in the Origin seminar. He gave a talk specifically for these features. So it's very nice. There's one problem is only the planet around G and K type star is more likely to see these features. So I'm not going to talk about these features. So the features I'm talking about is like this. So this is the paper by Borsa et al. 2021 on the Jupiter WASP-121b. So there are a bunch of the optical features like the sodium doublet, H alpha, there's also H beta, and the calcium H and K lines. It's observed by the espresso spectrograph on VLT. They observe 2 transits of the systems. And also for the same stars, same planet system, Cabot et al. 2020, who gave a talk last week, used the HARPS spectrum to also detect the H alpha and the sodium in this system. Because clearly you see the second transit has a much better signal to noise. So in the later part of my work, I'm going to compare my model with they call 4UT, this observation. Okay, and although compared to the helium, so this percentage is the percentage of the starlight. So this is a helium and Lambda alpha has a very deep transit depth. It blocks several planet radii. So for these features, it does not block as much as the Lambda alpha or helium, but for this system, hydrogen and calcium, both absorption already exceed the Roche lobe of the planet. So it clearly detects the outflow of the system. And also in 2019, by David Singh et al. Used the HST, is a PanSat project. They use STIS on HST to observe 2 transits in near UV. And they see the several magnesium 2, iron 2 features. And in comparison, this dashed line is the Roche lobe. So they also see strong absorption features beyond the Roche lobe, escaping from the atmosphere. And because they detect the magnesium and iron, it also clearly means the magnesium and iron are not condensate in the lower part of the atmosphere. And in addition, when we model the magnesium and iron, these atoms we can not only use them to trace the atmosphere, but they also have, this species also have the heating and cooling impact. So itself has the thermal impact to the atmosphere itself. So it's very interesting. And for the atomic lines, like H alpha, like magnesium, etc., there are over 20 systems have detected such lines, and the number increased very rapidly in the past 5 years or so. However, the theoretical work is kind of lag behind. So we really want to push this so we can get more information about the planet from these observations. And also, last September, there is a CubeSat led by the University of Colorado at Boulder. It's called CUBE. that specifically detect the near UV transmission spectrum of the exoplanet atmosphere. So we are going to have more information. So on the right-hand side, I have a table about the parameter of this system. So it's around surrounding of like F5 star with a very short period. The planet itself is very low density, it has very low surface gravity around a very it's ultra hot Jupiter. Okay, so I'll briefly outline the model and then I'll go into a bit more detail. So the hydrodynamic model we are using is a one-dimensional hydrodynamic atmosphere model generally used, developed by Koskinen et al. 2013. It includes photoionization recombination, heating and cooling, diffusion for each individual species, and also the escape. Because we already detect the H alpha, H beta in the atmosphere, so it's absorbed by the excited state hydrogen. We need a model to calculator to model the excited state population. So I'm going to talk about the Monte Carlo simulation of the Lambda alpha resonance scattering process to get the excited state hydrogen. And then we add a bunch of metal species into it. This metal species, not only we can maybe to detect it, but it can absorb some of this has a lower ionization threshold than hydrogen, so it can heat the atmosphere when hydrogen or Lyman continuum is already opaque. And also we have at the cooling, line cooling due to hydrogen, iron, magnesium, and sodium. Then we also, because our hydrodynamic atmosphere is kind of cut off at 1 microbar, so we also need a bottom boundary condition. I'll also briefly talk about that. So first, begin with the excited state hydrogen. Garcia-Muniz and Schneider 2019 create a model for Cal9b, which is hot Jupiter surrounding a type A star with slightly higher or quite higher surface gravity compared to WASP-121, WASP-121b. For this system, they have some quite interesting observation. So the plot here shows the model from 0.1 microbar to 10 to the minus 4-ish microbar and shows the several major heating and cooling channels. So the heating axis is kind of inverse, larger at the bottom. So the black solid line is the Lyman continuum heating that ionized ground state hydrogen and heat atmosphere, which is typically what's considered the major heating channel in the photoevaporation study. And this curve is the Balmer continuum heating. It's the Balmer continuum photoionized the excited state hydrogen. So they found at near this bottom of their model, 0.1 microbar is the Balmer continuum actually contribute more heating compared to the Lyman continuum, which typically not considered as an energy source in the photoevaporation study. So it's very interesting to study the excited state hydrogen. So this is a brief structure of the level, the 3 level, and also probably the ionized levels. That's the several most important in modeling them. The first is the 2p state has a very fast spontaneous decay to 1s rate. That's the major destruction channel for hydrogen 2p states. And for the production channel, the major production channel is the ground state absorb a Lyman alpha photon and then radiated excite. This channel is much more effective compared to, for example, electron collision excitation. So because of these 2 rates just dominate the production and destruction, so the 2p number density can just determined by ground state number density and mean intensity profile average mean intensity. So this is using the void line profile to average the mean intensity of the lambda alpha inside the atmosphere. Another state is the 2s. 2s state in the most part of the model, the dominant rate process is the proton collisional L mixing. So the proton collide like the hydrogen to jump between 2s and 2p. Typically, electron collisional has a larger rate, but just because these two has the same energy and just transfer the angular momentum, so it turns out the proton has a way larger cross section, and the rate is also about the other magnitude larger compared to the electron collision. And this rate is turned out is quite big, so 2s and 2p is reached a collision equilibrium in most part of the atmosphere. Then to solve the excited state hydrogen problem, the major problem is to solve the lambda alpha intensity. So lambda alpha goes through a resonance scattering. It means in the rest frame of the hydrogen atom, the absorbed photon frequency is almost identical as the scattered photon frequency. So if you shift to the left frame, the absorbed frequency has a strong correlation with the out scattered frequency. So if when the lambda alpha photon is scattering inside the atomic hydrogen atmosphere, it not only scattered in the physical space, it can also scatter in the frequency space, because when it goes away from the line center, the scatter one is also most likely at the line. If you go to the line wing, the scatter one is always at the line wing. So in the right hand, this is cartoon. The y-axis is the physical space, and x-axis is the frequency space. Assuming we have a lambda alpha photon somehow created near the bottom here, it wants to escape. A typical line center object depth for lambda alpha is like 10 to the 8. So if we just at the line center try to escape from the random walk, we need to scatter like 10 to the 16 times. It takes forever. But with scatter an order of tau times 10 to the 8 times, it can go to a line wing where the optical depth is the order of unity, and then it can escape physically very fast. So the emitted lambda alpha typically has a dip in the center because of this effect. So in the Gaussian-Moniz work, because the physical complicate of this resonance scattering problem, they only use basically assume a complete redistribution. So for every scattering, they assume the photon just emit with the void profile center and the line center. Then they can write a radiation transfer equation combined with the model to solve the lambda alpha profile. So in our work, we chose to use a Monte Carlo simulation. In the Monte Carlo simulation, we have the partial redistribution I just talked, and also include the polarization. Lambda alpha can have three original sources. It can be a stellar lambda alpha input from the top of the atmosphere. Their lambda alpha can also generate internally. When hydrogen recombine, typically we have the case B recombination so it eventually recombine to the n equals 2 states, and then it will emit a lambda alpha. So every recombination, it will emit a lambda alpha. Also, there can be a collisional excitation to emit lambda alpha. So there are external source and internal source. During the scattering, it can eventually escape from the top of the atmosphere, or there have sink inside the atmosphere. It includes if the lambda alpha can ionize, for example, sodium, potassium, magnesium. So if we hit this metal, then it will get absorbed, and also absorbed by the molecular hydrogen quite efficiently. But molecular hydrogen only exists roughly near the bottom boundary. So effectively, we have an absorbing bottom boundary. when before excited state hydrogen emit another lambda alpha, it may collide with the electron and transfer the electron to the transfer the energy to the electron. So that's the collisional de-excitation. It's also a heating mechanism to the atmosphere. The excited state hydrogen can also go to a two-photon decay to destroy this lambda alpha, break this scattering channel. So with this Monte Carlo, we can model the lambda alpha intensity. So this is an example of the result. We have split the mean intensity into three original sources: the external stellar source, recombination, excitation, and the sum of them. To save the computation time, Monte Carlo typically have a lot of fluctuation like this. So I also do a spline interpolation for the sum of them. It tracks the original shape, and you can only see it when you really zoom in. Okay, so that's the excited state hydrogen. Then the metal species not only can have a photoelectric heating effect, it can also have a cooling effect. I'll use one example, the magnesium-2. This is most typically the strongest metal cooling features. So the electron collisionally excites the ground state and to excited state, so it can emit delta E and times the collisional excitation rates. That's the total cooling rates. So for magnesium-2, they have two electric dipole transitions. So the sum of these two transitions, we get the total cooling rates versus the temperature. We also compare our result with the Knight and Furlan 2012 paper. They use the ISM code cloudy to calculate the cooling at several temperatures and agrees relatively well. So magnesium-2 is relatively simple and its rate is large. We also have the iron. Iron is much more complicated because the level population. I'll just skip the details and in this talk. Then we have the bottom boundary problem. So Michael Evans 2019 used secondary eclipse. It observed secondary eclipse of the system, and they model a temperature profile from 10 microbar to 10 bar. That's the dashed line. So we use this temperature profile and feed into the hydrostatic photochemical model based on the Lavas and Koskinen 2017 paper to construct a model for including the molecule species and the ionization. It also includes the condensation, so we can get the radius versus pressure, and we already have temperature profile. We can have the number density of each species. And to get the radius, we also need an anchor to compare to the planet radius. In our model, we set at 4 millibar at it's the transit radius. Later on, to confirm this number is a reasonable one. And in addition, because we already see a very abundant iron in the upper atmosphere, the iron is not condensate. But if we use the original temperature profile, the iron will, the temperature will go below the condensation temperature. So we adjust the bottom part a little bit higher and just say the difference is much smaller than the error bar in the Michael Evans paper. So with this, we can get, and also at the hydrodynamic model is done at 1 microbar. They connect at 1 microbar, and in this part, because the Michael Evans only go to 10 microbar. So in this region, we just kind of smoothly connect the hydrodynamic temperature to the lower part. Okay, so have some result, hydrodynamic atmosphere model result. First is the temperature profile. Have the now it's the radius in the axis, and also have the pressure on the top. versus the temperature in the black solid and the outflow velocity in the dashed line. And we also mark the sonic point where the outflow velocity equals the adiabatic sonic velocity and the star radius at here. Using this outflow velocity and the number density, we can calculate a mass loss rate. So it will give about 5 times 10 to the 12 grams per second. It converts to 7 10 to the times 10 to minus 11 planet mass per year. So I like to compare this mass loss rate with the energy limit energy limit escape rate. So there are like 2 methods to calculate this rate. Most people is using this formula, so it's simpler. Just the LXUV is the Lyman continuum luminosity. It times the surface of the planet, assuming a complete redistribution of the heat. And this heat will convert to a gravitational potential to let the particle escape from the surface of the planet. So with this equation, it gives 10 to the 13 grams per second. However, there's I think more physical expression because the heating of by the Lyman continuum photon is typically not at the surface of the planet, it's at much higher up. So we have a equivalent or most effective heating radius by the Lyman continuum, that's this RE. And from that radius to the escape, that's the potential difference is this delta U. So that's from that radius to the L1 point. Using this formula, I'll get a much larger number here. So yeah, typically I don't have the efficiency. Typically there's a epsilon efficiency times here. So the RE here, for this one, we have about 1.45. We can see it from this plot. So that's the dominant heating and cooling process. The peak heating is at about 1.4. So in this plot, we have, again, against the, this is the heating and cooling against the radius. So solid lines are the heatings and dashed lines are coolings. By the way, the Balmer continuum heating is already included inside the photoelectric heating, I guess plotted separately. In this model, the Balmer continuum is not the dominant heating channel anywhere. For the cooling, we have this is a Lyman alpha line cooling and also the magnesium 2 line cooling. It can be very important in the close to the peak of the temperature. And at the outer part of the atmosphere, then the adiabatic cooling is the dominant one. And for the ionization and recombination balance, so this plot shows all the channels that can ionize hydrogen or recombine a hydrogen. The solid line is channels that ionize the hydrogen. And the dashed lines are channels that recombine hydrogen. So for all this race is the charge exchange from all this metal or helium with hydrogen. So if it's shown in dashed, it means it's the net effect is to recombine a hydrogen. And separately, they also have a dotted line. That's the ionization from the excited state hydrogen by Balmer continuum. Also, this is included in the total photoionization of hydrogen. But you can see in the bottom part, actually the Balmer continuum ionization is the dominant channel to ionize hydrogen. So it determines the ionization balance near the bottom. Okay, we can have a number, several important, the number density of several important species. And now we combine the number density from the lower photochemical model and the upper hydrodynamic model. So this color shows the region of the basically here shows the boundary of 1 microbar and the hydrostatic model and hydrodynamic model. And we see the species number density, although it's from 2 separate codes, most species has really the number density connected relatively smoothly. And also for the majority part of the hydrodynamic atmosphere, all the species are quite highly ionized. We have excited so 2pC hydrogen here, and we see it drops relatively fast, and I'll comment on that a little bit later. So use this number density profile, we can calculate the transmission spectrum. So this is the transmission spectrum based on that model. We see we have a very strong magnesium-2 doublet. The line center go over 50, that's 50% of the star radius at the high resolution. And this dashed line shows the location of the Roche lobe. We have a lot of features outside the Roche lobe. And so for my, I'll have a more explanation on how to calculate this transmission spectrum, especially some lower level is now the ground state. For magnesium, there's just this magnesium 1 line that's from the ground state. So it have a electric dipole connect to this level. So in our calculation, we assume all this level and above is completely depleted because it has a fast radiative decay to the ground state. That's much faster than collisional excitation, so it's not in LTE. And for this, there is a semi-forbidden transition connect to the ground state. So we have the collisional rates and the spontaneous decay rate. So we construct a 2-level population problem and get the excited state number density. So we have some weak magnesium absorption features, magnesium 1 features like at here. That's have these states as the ground state. Another interest species is calcium 1. So I got this Gaussian diagram from this more 1968 paper. So this is, I checked this is basically the same as the NIST database. One problem that puzzled me initially is the transition between this 4P and 3D. So this transition here, it satisfies all the electric dipole transition selection rule, but it's not in the NIST database. And then I asked in astronomy group why that's it, and one guided me to a 1950s paper to detect the intensity of the calcium 1, and that's actually they have a quite strong line between them. So, and just told me the NIST database is not complete for the heavy metal. So, and because of this strong dipole transition rates, so again, from this level and above, we assume it's not it's completely depleted. And also for this level, because it has a relatively strong radiative decay rate, although it's a semi-forbidden transition, it turns out the excited states number density is very low. So for calcium 1, there is only one line that's if calcium exists in the upper atmosphere, that's this 4227 transition line. I see some other observation work trying to detect some other calcium line, especially from excited states. So I believe that's it's very all the observation turns out negative. So I believe there's no chance to detect any calcium 1 line from excited states. And then if we zoom into just the continuum, let's say the Y scale. So with the continuum at the UV part is determined by the radius scattering, and at the infrared, it's mostly the H minus continuum absorption, and the dashed line is the transit radius. So we have our model pretty well matched the planet radii. So that's where to confirm our 4 millibar pressure is at the planet radii. So that's self-consistent. Okay, then so I'll compare the model with the Davidson near UV transmission spectrum. So that's from 2300 to 3000 angstrom-ish. So we can convolve our model with the resolution of HST and then box it into a 4 angstrom beam, just like what they did in the paper. And this is the black line and the dot is what we have. Although, like we said, the magnesium is already over 50% of star radii after the convolution and the beam. It's we underpredict the magnesium features, and all the other features is too small because of this. So it should be because the absorption line is too narrow. So after the smooth is basically gone. This is already after we have the outflow, include the outflow of the atmosphere. So when the atmosphere outflow, it can have a line of sight component. It can broaden the line. And we also include the spin of the planet. We consider it's a tidally locked, so it has the same rate as the orbital period. And it also have a kind of broaden effect. Even include these two broaden effect, it's still too narrow to compare with the observation. And for the optical features, I just picked these few strong features. So for the calcium, now the optical observation has a much higher resolution, so I don't need to do any convolution of being this is the original resolution. So for calcium, you can see clearly the model is too narrow compared to the model, compared to the observation. The H alpha and H beta actually is too strong, and in the model, you see the H alpha is quite more stronger than H beta. It means the excited state hydrogen number density is decreasing quite smoothly outward. Then both features, so the ratio of if it's uniform number density, then the peak, basically just the ratio of the cross sections. But the model actually suggests it's quite similar. That's because I mentioned earlier the excited state have a sudden drop, and then both features, the line center transit depth basically mark the location of that sudden sharp drop. So clearly this model does not fit the observation well, and we should see what physics we are missing. So there's clearly a big elephant in the house. That's we haven't included the Roche potential or the tidal distortion. The planet has a very low surface gravity. So on the left hand, this is a to scaled cartoon. I showed the Roche lobe and the surface of the planet. It's already almost filled the Roche lobe, and you can see it's already elongated. So, and this is the view from the top, from the North Pole, and the right-hand side is a view from basically from the telescope. So the background circle is the star. That's all to the scale. The center filled black circle is the planet, and the blue circle is the Roche lobe. Then there are two circles to mark the equipotential surface in Roche potential. Because of this distortion, actually I'll call the direction towards star is X. Then toward the orbital direction is the Y, and to the pole is the Z. So Y direction actually have about 2.5% longer than the Z direction. So when we observe the transit, even in the optical, actually we see a roughly elliptical shape. So when we now we try to have the include the tidal effect, we also correct this effect, and it turns out just a little bit of difference in radius makes a very large impact on the result. So then we include this tidal potential because we are only have a one-dimensional. We just model the substellar direction. So with that effect input, the temperature profile becomes completely different. Now it actually initially goes down to almost 0 for a large section and then go to a high temperature region. So we also mark the location of the Roche lobe. It's right here. It's basically the same location as the sonic point, and the star radius is here. So the thermosphere of this system then is completely outside the Roche lobe. So using this velocity, we can assuming if it's uniformly mass loss, then it will be 5 times 10 to the 14 grams per second, or almost 10 to the minus 8 planet mass per year. So because actually the mass loss will not be spherically symmetric with the tidal potential, so the actual value is probably more like half of this value. Again, compare with the photoelectric, the energy limit escape, all these values is now changed, so it's still 10 to the 13 grams per second. If we use the other way to calculate, because the peak of the most energy depth is absorbed outside the Roche lobe, then the delta U actually is negative, so it doesn't really make sense using this method. If using this model, basically all the features becomes much stronger because we have higher outflow velocity and higher number density. The magnesium.
Sorry, can I just ask a quick clarification question?
Sure, go ahead.
Yeah, I just didn't quite understand how you were including the tidal force there in a 1D model. You were choosing the direction through the L1 point, or what direction are you choosing?
Yeah, I choose the direction to the L1 point, and in the gravity, we just add actual potential caused by the Roche potential in the gravity part.
Okay, and do you think that's representative of a spherically averaged result, or?
Yeah, it will be very tricky to how to map the substellar direction to the other part, but that's what we can do right now, basically.
Okay, thanks.
Yeah, and so from the substellar number density to get to this calculated transmission spectrum probe the terminator. So we assume the number density is equal along the equal potential surface. Basically, then so we can map the number density in the substellar direction toward the terminator and then making this plot. So I didn't mention, so I can calculate the chi-square of this system. So previously, without the tidal force, I think it's 1.7, if I remember correctly. So now it fits better, especially for the iron, it actually fits good, but it overshot the magnesium. And for the optical features, it's all way too large. So there's no way to be correct. It's way too broad and too strong, and just doesn't make sense of this comparison. So then we try to tune our parameters to find the in the meaningful, because a lot of parameters actually have a very large error bar, so we adjust of them. So this is several best match model. So this was the observed physical parameters. So we adjust the radius of the planet. So there is the 1 sigma is 0.044. So I just use this radius minus half of this sigma to this planet radius and keep the planet radius to star radius, this ratio constant. That's directly observed from the transit depth, and we keep the period, the constant, and the ratio of the ratio of star radius to the semi-major axis to be constant. So that's the duration of the transit, and then we keep the planet mass not changed. So just using this method to slightly increase the surface gravity, and also it turns out to better match the line profile shape. We also need to decrease the Lyman continuum by a factor 5-ish, but that's just actually it's not really change the line center transit depth. It's more about the line profile shape, and also we need to reduce the stellar Lambda alpha from our fiducial value by 40%. So that's I call it this best match model. So again, this is the best match, the heating and cooling profile of the best match model. So again, the Balmer continuum is not is not the dominant heating channel. Actually, over here, it's the metal species is the dominant heating channel. That the metal heating is not included in the Garcia-Moniz work. So with this model, we have the mass loss rate is much lower now. Just change the radius by half sigma, 2%, or a little bit less than 2%. I think just a little bit over 1%, the radius, and then it's from 10 to the 14 to 5 times 10 to the 13. And because I reduced the Lyman continuum flux, so this number decreases. Again, the peak heating is outside the Roche lobe, so this method does not make sense. Yeah, and for the cooling channel now, previously without the tidal, we have the magnesium 2 and the hydrogen Lambda alpha can play an important role, but with the tidal, just the adiabatic, basically all the hydrodynamic rates dominant all the cooling. So actually the line cooling is not important in this case. And for the ionization recombination, again, actually the Balmer continuum ionization is the dominant ionization process in a quite large region near the base of our model. So typically we have like a case A recombination, case B recombination. If the Lyman continuum is optically thick, this will be the case B recombination. For this case, actually, so if it recombine, we need the Lyman alpha to really escape to make it effectively real recombine. So that's the outcome of the ionization is dominant by the Balmer continuum. And yeah, okay, so I think I passed this one. So go to the transmission spectrum. So this is the near UV part. The chi-square is similar. So we also need to boost the iron abundance by a factor of 6 to match the iron features here. The magnesium feature, magnesium abundance is just a solar atmosphere abundance, and it matches the observation well. And there's the magnesium 1 features. So the signal to noise is not high enough to really see these features. And for the optical features, basically I can fit all the features quite nicely. Yeah. Okay, so we have a model that fits most of the features. So leave this somewhat express the real physical features. So we see the mass loss is actually mostly driven by the Roche lobe overflow rather than the photoevaporation. So my advisor Koskinen just published a paper recently. So just show that for the very close-in planet, so the dashed line is the mass loss caused by the photoevaporation for a Uranus-like planet. And when it go to about 0.03 AU or less than 2 or 3 days, then the Roche lobe overflow, this solid line, actually becomes the dominant one. So our model is agree with this conclusion. Okay, so that's my summaries. So we developed a model for the hydrodynamic escape that includes metals such as magnesium, iron, and excited hydrogen. And we can broadly reproduce all the observed features of WASP-121b. We show that the Roche lobe overflow is very important in the mass loss rate for this system. And the very deep ionized iron actually cannot explain without the Roche lobe overflow. And the photoionization from the excited state is important in determining the hydrogen ionization fraction. And the metal species photoelectric heating is also very important. Cooling of magnesium and iron can be important part for, it's not important for our final model, but it can important for planet has a higher surface gravity, for example, the Cal9 system. The strong iron and magnesium absorption feature suggests the iron and magnesium is not condensate in the lower part. And also the Roche lobe overflow is the Roche lobe overflow can actually explain the most part of the sub-Neptune desert. We don't really need the photoevaporation to explain the sub-Neptune desert. Okay, thank you. I would like to take any questions.
Klaus? Okay, so any question? If you have a question, please raise your hand so that I can actually see from here. Yes, Everett.
Yeah, these are great models. I was just wondering for the energy limited, whether it makes sense to calculate that accounting for some cooling, because I see you have the adiabatic term that cools. I was wondering if the energy limit, it has the gravity and it has the input radiation, but if it should also have like the cooling of the gas as it expands.
Yeah, so because the energy limit, that expression is very simplified. So there actually should be a lot of physics behind that, and everything is basically hidden in that epsilon, that coefficient. Yeah, like you said, there's a cooling effect where the Roche lobe, that the gravity potential is not from the surface of the planet, and also not only the Lyman continuum can heat the atmosphere, like the metal species using lower energy photon, like the Balmer continuum, all can heat the atmosphere. So there's a lot of caveat there, and it can vary a lot from system to system according to the model. At least for this super hot system, it can that constant can vary a lot. It contains a lot of physics in it.
But in the end, it seems to do pretty well between your 1D and your extreme, the other extreme of the Roche lobe towards the star.
Pretty
was
well.
just-
Yeah.
I was just noting the rate was this.
The feet
Yeah, this one.
or
Is it this one, Everett?
Oh, no, I was just saying that the mass loss rate of the energy limited,
oh
the really simplified energy limit, it seems to bracket between your first model you showed, which was a 1D model, not accounting for any Roche lobe, and the other was the maximum limit, upper limit to the mass loss. It's somewhere in between those. It doesn't seem so terrible, even though it's so simple.
I don't have more insight about that. Maybe it's a coincidence. I never really think more about, but typically I think the people assume the Gibbs-Land coefficient is less than 1, but at least for this case it's larger than 1. Yeah, maybe I don't know how reliable that matter is. I don't have more comment on that.
Well, thank you.
Okay, any other question? So I have a question, the Andrew first.
Go ahead, Serena.
Yeah, no, I have a very naive question. I did not know that Roche overflow is such an important thing. So all these are near very hot Jupiters like this. Would you think the erosion of overflow would be very important for all those sorts of cases? Similar kind of cases for other exoplanets. Okay, so we need to actually, so I can hear that from a year later. But Andrew and Maitri, I think, Madeline. So I think we'll have to answer you separately in person. Could you actually, Andrew, could you actually write your question in chat, then we will get back to you because there is another meeting going on at 1 p.m. I need to back at this room. So thank you for attending, and Andrew will get back to you in person.
Sounds good. Thanks.
Thank you. Oh, cool. Okay, let me